Okay, welcome back. So the idea is that you will have gone through the supplementary notes and supplementary lectures on biological vision before continuing with the main content of this chapter. So we're going to talk now about color versus monochrome images. So of course, although we perceive the world in color, monochrome images, or that is images in which we've removed any notion of a dominant wavelength, we'll talk about that in a second, contain a huge amount of information. Now, monochrome images, which is the term monochrome is a fairly old-fashioned technique that comes from old-fashioned term that comes from photography. A better term would actually be achromatic because we don't have a dominant color, so there's no dominant chroma value. But yeah, monochrome or achromatic images, also known as grayscale images, contain a huge amount of information. And often, when we are developing some algorithm for image analysis or computer vision, we will we will be able to make use of of purely achromatic information. That is, we can often throw away the color in some fashion and just work with a what is an achromatic image, which is a sort of a brightness modulated spatial field. So it's just a function of space over which we have one value rather than a bunch of color values, but one value which tells us about the brightness at that point in space. Now we sometimes, well, in image processing, we often refer to these as grayscale images. And there are lots of algorithms for going from color images to grayscale images, depending on what aspects we want to preserve about the full color information when we convert to grayscale. So there are different ways in which you can define a grayscale value based on a color value. So the term gray level is quite widely used to describe the quantity of achromatic light intensity at a particular location in a monochromatic image. And we'll discuss this a bit more as we move through this lecture and also the practicals associated with this. So we're throwing away information, of course, if we convert a color image into an achromatic or grayscale image. So what is the information we're throwing away? Well, it's the color information, right? But what do we mean when we talk about color? So one of the nice ways of thinking about what we mean by color is to introduce a color is to think about color as being a kind of a having a being some having some geometric space associated with it, and we can have different dimensions to the space, but three is fairly natural for a number of reasons. And so the examples of color space that you will encounter will be RGB, CMY, YIQ, and HSI. I mean, actually, there's a whole bunch of different color spaces, but these are ones that I think are worth knowing about. All right, so let's start with the RGB model. So the RGB model is just based on a simple notion of, let me just get my right screen here. Here we go. Right. So it's based on the notion of having a three-dimensional Cartesian space. So in fact, let's make that a different color. Try if I can convert this color. Oh, looks like I can't, so let's get rid of this. Let's try that again. So we're using black for good. Okay, so right, so let's get our Cartesian space in here. Oops. Right. So here's one axis, here's another axis, and here's our third axis. So this is going to be So this is going to be the red axis, this is going to be the green axis, and this is going to be the blue axis. So we have RGB as our three-dimensional color space. Okay, so that's what that looks like. Oops, let's go back here. Right, so we have our RGB. This is the RGB model effectively uses these three axes, and we can talk about an RGB color cube as defining the shape of this space. So let's have a look at what that looks like. So we've got the three axes, but now what we're going to do is define a cube that sits in this color space. What color am I going to use for this? Let's try, don't want to use red, green, and blue because that will be confusing. So let's use yellow and hope that shows up reasonably well. So, well, it's not great, but it's not terrible. Oops. Right. Okay, so I'm gonna use, I guess I'm gonna have to go for black on this. So let's create our RGB cube then. So here's one axis, one side of the cube. There's another edge of the cube, and then we extend this out like so. There we go. And drop down here, come across here. As you will see, I'm fairly appalling at being able to draw, but at least this is coming out better than if I do it on a blackboard or whiteboard. There we go. All right, that's sort of cube-like, right? So here's our RGB color cube, and the space that we have here is extends from 0 to 1 on each of these three axes. So the origin of this color space is here. So this is the origin, and that point will have coordinate down there. It will have coordinate 0, 0, 0. This point here has coordinate 1, 1, 1, and we effectively move between 0 and 1 on each of these three axes. So 0, 1, and that's 1, and of course we have 0, 0, 0 in here. Okay, so hopefully that's clear enough. So this location here, of course, corresponds to red is equal to 0, green is equal to 1, and blue is equal to 1. Okay, so that's that corner there, and then you just cycle through the different coordinates for the corners of this cube. Okay, so for something like this, any color will lie somewhere in this space, and the range of values that we have for all three colors is 0 to 1. So 0 means no intensity, so intensity is 0, and 1 means maximum intensity on that color, whichever axis it happens to be on. So all the possible colors that we can conceive of will lie somewhere in this space. Now this is not a bad space for talking about the display of colors on a computer monitor, and in fact many software packages will use this range of values between 0 and 1 to specify colors on the display. If you think about why that's a natural thing for computer displays, it's pretty clear. So red, I mean, many computer displays, color displays will have three um, three three uh, components, or three diodes, or three organic LEDs, or what have you, that occupy a very, very, very small space on the screen. Um, and those three LEDs might be, so you can have one LED that will do all three colors, but it's more common that you will have three separate LEDs that will display red, green, and blue separately. And then by combining the intensities of red, green, and blue and blending them together, you basically get any color in this color space. And so each LED is going to have a red, green, and blue at one point in space on a display, is going to have values that go from 0 to 1. Okay, now in this color space, there is, you can imagine drawing a sort of a line between 0, 0, 0. Oops, that's slightly curved. Let's try to get that a little less curved. There we go. Inadvertently erase something as well, but let's try here again. So between 0, 0, 0 and 1, 1, 1. There you go. That's a much straighter curve. So you can define a straight line along which, so along this line, so this line has R equals G equals B. So it's a straight line in three-dimensional space from 0, 0, 0 to 1, 1, 1. Okay, that line represents the line of grayscale values, or if you like, achromatic values. Okay, so achromatic because there is no dominant color based on this red, green, blue color space. All three components are equal in intensity, and that gives us the fairly consistent, obvious notion of achromatic. So that's the grayscale color space within the RGB color space, and you're going to be looking at how to create, or how, what that means in terms of displaying images when you get on to the practical, the associated practical for this. Okay, so R equals G equals B equals G. That's one of the most common, red, green, and blue color spaces, and the RGB color cube is one of the most common color spaces that you will find. It's very natural for working with digital image data. Now, there is another color space that you can derive from RGB, which is nonlinear, because it consists of a ratio of values. And so if you've got a point in the RGB color space defined by a certain value of red, a certain value of green, and a certain value of blue, so a coordinate in RGB space, then you can convert that into what are known as trichromatic coefficients, also known as a normalized RGB space, by performing the calculations shown here. So you take a ratio between the red value at any point in that space and the sum of red plus green plus blue. Okay, you can also do that for the green value. So take a ratio of G over R plus G plus B, and then for a third component of this trichromatic coefficient, you take B over, you form B ratio, the ratio B over R plus G plus B. So in doing that, what you get is, it's not a very intuitive color space, but you will see that actually this color space gives us a representation of visual data, and in particular of color contrast, that is more similar than RGB space to what we perceive as being a certain color or color contrast. So don't forget this. We're going to meet this calculation 3 times, or 2 times in the practicals. It's very important to look at this. The reason, although this is not very commonly used, the reason that I present it is that it's a very simple definition. So you don't need any complicated algorithms to work these out. It's the very simple ratio. But yet it gives you an insight into some advantages of the other color spaces that are more complex to calculate. So this you can work out yourself. The other color space conversions so from RGB into some other type of color space, such as hue saturation intensity, or hue saturation variance, or any of the other multiple weirdly shaped color spaces, is not that intuitive, and it's not easy to do on one's own. So I recommend using this. I've also found situations where other color spaces that we'll meet in a second are the norm, but I try this and it works better. So it's a really good one to use. Okay, so this normalized color space model is sometimes called normalized RGB or NRGB, and it can be very useful for pattern recognition, object segmentation based on color. But if it comes to displaying an image, you would never use NRGB. You would always use RGB, or perhaps you might use HSI, depending on the type of display. Or if you're, let's say, using printing an image, you would tend to use something like CMYK. Okay, so that brings us on to the CMY model. So CMY stands for cyan, magenta, and yellow. And these are known as the secondary colors of light, for light. They are the primary colors for pigments, or in other words, inks and printing. And so you will find this color space used in printer technology. If you've got a printer at home, you will know that it will take ink, and often the ink is separated into either into 4 cartridges, so one for black, one for cyan, one for magenta, one for yellow, or sometimes one CMY cartridge and one K cartridge, which is the black cartridge. So these colors work on a subtractive principle, so they absorb components out of the light spectrum, which is why they are fundamentally different. Many older color printing devices require CMY data, but most printers today will have inbuilt the ability to convert from one color space to another on the fly.